Welcome back, guys. Today we're going to be looking at our last topic for the permutations and combinations unit, and we're going to be looking at problem solving with permutations and combinations. So before we get into the examples today, I'm going to take you on a quick journey back through all that we've done in this unit. And so these are all of the things that we're going to have to keep in mind when we're solving word problems. So we started off with the fundamental counting principle. So we were looking at the number of ways we could arrange an object. A set of objects. So for example, if we had 5 books on a bookshelf, we would have 5 times 4 times 3 times 2 and so on. We can represent that in factorial notation. So 5 factorial would have been 5 times 4 times 3 times 2 times 1. Ultimately, what we're doing is we're taking the 5, multiplying by 1 less than 5, and then 1 less than 4, and then 1 less than 3, and so on. That led us to permutations. And so when we were looking at permutations, we were looking at things where order mattered. And so with permutations, order mattered. And so our formula was n factorial over n minus r factorial. We also used that factorial notation to solve for some unknowns, where we took n factorial over, say, n minus 2 factorial, and we broke it down to get an expression. We're not going to be looking at that today with regards to the word problems. One thing that then we had to deal with was repetitions. What if I have repeating letters? And so when there's repeating letters, you have to remember to always divide by your repeats. And so that was really important because if we didn't divide by those repeats, we'd have too many combinations. And so you have to divide by your repeating letters or repeating digits, repeating elements. So for example, if I had tattoo and I wanted to rearrange all the letters in tattoo, well, I would have to consider how many T's were repeating and how many O's were repeating, and I would divide by those. When we got into combinations were examples where order did not matter. So with permutations, we were looking at arrangements, distinct arrangements. We were looking at executive committees or placings. With combinations, we're looking at ways that we can select something. So one of our keywords was select. So up here, one of our keywords was arrange. And down here, one of our keywords was select. And today we're going to be looking at an example where we have to select and arrange. And so we'll get into that later on. So when we're doing our word problems, it's really important that we read carefully and we know what the question is asking. Obviously, one of the most important pieces is to decide, does order matter? If order matters, then it's permutations. If order does not matter, then it's combinations. We also have to ask ourselves, is repetition allowed? So for example, if we were looking at a telephone number or a license plate, we have to ask, can we use numbers more than once? Can we use letters more than once? That would change our number of choices. So that's important to check for. When we're solving problems that involve restrictions, you always need to deal with those restrictions first. So it might be that we're selecting a committee and a certain person has to be on the committee, or we're arranging people into a photograph and certain people have to be in certain positions. Those would be some restrictions that we deal with. And again, I can't stress enough, whenever we're doing these questions, make sure you know whether order is important or not. All right, so let's get into some examples. Now, throughout this lesson, or during this lesson, I only have 3 examples in this lesson, but after the lesson part is over, I'm going to talk through some examples from the assignment. So feel free to do the assignment first and then come back to check your answers. But I've chosen some questions from the assignment that typically I get some questions about in class. All right, so the first question says, how many arrangements of the word poppies can be made under each of the following conditions? So if we have no restrictions, we'll start by writing out the letters. So poppies, P-O-P-P-I-E-S. So if we look at the word poppies, we have 1, 2, 3, 4, 5, 6, 7 letters. So we've got 7 letters, and there are 3 P's. And so if we were to arrange this, we would have 7 factorial divided by 3 factorial. So those would be our 3 repeats, and that gives us 840. Now, what if each arrangement has to begin with a P? So I got P-O-P-P-I-E-S. Well, ultimately what I'm going to do is I'm just going to take one of the p's out of the equation. So I have to start with a p, so I know my first letter is a p. It doesn't matter which p I pull out, it's still going to look the same. So I pull out the p and I'm left with 1, 2, 3, 4, 5, 6 letters. So 6 factorial, but I have 2 p's there still. And so 6 factorial divided by 2 factorial is 360. Sometimes you'll see that 1 in front, just to represent that we've pulled out that 1p. Now, if the first two letters are p's, again, we're starting off with poppies, so Poppies, but we're going to start with 2 p's. So we're just going to pull 2 p's out of the equation. So one way for that one way for that one, and then we're left with O, P, I, E, and S. Well, that's 5 factorial. And because we've taken 2 p's out, there's no more repeating letters. So that's our answer. 5 factorial is 120. Now, what if all of the p's have to be together? Anytime letters have to be together, we group them together in brackets and we count those as one group. So P, 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 or we count them as one element. So P, 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 and then we've got O, I, E, and S. So that gives us 1, 2, 3, 4, 5 factorial times there are 3 factorial, so 3 ways to arrange those p's, but those p's are all repeats of each other, so that ultimately gives us a 1. So we're left with 5 factorial times 1, which is still 120. Now the last example, it says, how many ways can we arrange these letters if the first letter is a P and the next one is not a P? So again, we've got poppies. First letter has to be a P. So we're going to do the same thing as before. We're just going to pull a P out of the equation. So Poppies. We're just going to eliminate that P. And then we have not a P. So that means we have to have an O, an E, an I, or an S. And then that leaves us with 5 remaining letters. So these here would be the 5 remaining letters. Now, of those 5 remaining letters, we have 2 P's. So we have to consider there's still some repeats there. So one way with the P, because we're just pulling that out, there are 1, 2, 3, 4 letters to choose from. And for this last part, we have 5 remaining letters, but 2 repeats. So if we were to write that out, it's going to be 4 times 5 factorial over 2 factorial gives me 240 ways. Now, if you look, we're using factorial notation the entire time. We're arranging letters, so this is an example where order matters. So if you want to write that up here, this is an example where order matters. So anytime we're dealing with factorial notation, that means there's some type of order. Now the next question here, it says a class consists of 5 girls and 7 boys, and a committee is to be formed consisting of 2 girls and 3 boys. Determine the number of ways a teacher can choose the committee. Another way to say choose is select, and we're dealing with a committee, not an executive committee, but just a committee. So this one, order does not matter. All right, so if there are no restrictions, that just means we've got 5 girls, we want 2, we've got 7 boys, we want 3. So we want 5 females, or sorry, we have 5 females, we want 2. So we want 2 females, and we want 3 males on the committee. So that means that we have 5 females, we're choosing 2, and we have 7 males, and we're choosing 3. And so that would give us 10 times 35 is 350. Now, what if Sarah has to be on the committee? Well, we take Sarah out of the equation. So Sarah has to be on the committee. That means that we have 4 remaining girls to choose from, and of those 4, we want 1 more. And the guys, we have 7 guys, and we still want 3. So it's going to be 1 times 4 choose 1 times 7 choose 3. So 4 choose 1 is just 4. 7 choose 3 is 35. So there are 140 ways to select the committee if Sarah has to be on the committee. All right, now this next example is a little bit different. So it says Brandon and Randon cannot both be on the committee. Well, there's two ways that we can approach this problem. One is to consider all the ways Brandon can be on the committee, then consider the way Randon can be on the committee, and then figure the way that neither of them can be on the committee. So we can say Brandon on the committee only, or Randon on the committee only, or neither. So it says they cannot both be on the committee. So that means either Brandon's not on the committee, or Randon's not on the committee, or neither is on the committee. So this is one way to look at it. So this is option 1. And then we're going to look at another way to look at this in a minute using complements. So Brandon only on the committee. Well, if only Brandon can be on the committee, then we still have the 5 females and we're choosing 2. That's not going to change at all throughout this question. Brandon gets pulled out. So there's only one way for Brandon to be on the committee. And so if Brandon's been pulled out and Randon cannot be on the committee, that only leaves us with 5 males to choose from. And since Brandon's already on the committee, so we could write 1 choose 1 if that helps. Since Randon can't be on the committee and Brandon's already there, we have 5 choose 2. So notice we have 1 plus 5 plus 5. Now you could think about it this way as well. You could say, well, Brandon has to be on the committee. Randon can't be on the committee. So one Brandon choosing 1 Brandon, 1 Randon choosing no Randons, 5 females choosing 2 females, and 5 males choosing 2 males. Well, if we add that up, we've got 1, 2 plus 5 gives us 12, which is what we need, and 2 plus 2 plus 1. So the 1 choose 0 and the 1 choose 1, we're just not writing those pieces out. Okay, so again, if I were to write this all out, I would take Brandon out of the equation, and so I would have Brandon being on the committee already. That's the 1 choose 1. That leaves us with the original 5 choose 2 for the females. For the males, we now have 5 males left in the committee to choose from, and of those we want 2. So if we're not writing out those other 2 pieces that I crossed out, you won't see everything adding up, but ultimately this is the key information. Now, if Randon can only be on the committee, the girls don't change, so 5 choose 2. Just like Brandon, Randon's already on the committee, and Brandon cannot be on the committee, so that leaves us with 5 males to choose from, and of those 5 we want 2. Now, what if neither of them can be on the committee? Well, that's like having Brandon and Randon, and we're choosing neither of them. And so we have 5 females choose 2. That doesn't change. But we only have 5 males to choose from. But because neither Brandon or Randon can be on the committee, we need 5 choose 3. And so if we multiply this all out, 5 choose 2 is 10. 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 10 and 10. Now you might be wondering, well, wait a minute. You have 5 choose 3 there. Why does this say 10? If you remember from our last lesson, 5 choose 2 and 5 choose 3 have the same value because in combinations, if our R values add up to the total, they're going to be equivalent. If you remember from before, 7 choose 1 would be equivalent to 7 choose 6. 8 choose 3 would be equivalent to 8 choose 5. So that goes back to our last lesson. Now, if we multiply this all out then, or add it up, we've got 100 plus 100 plus 100. There are 300 ways to have that committee where Brandon and Randon cannot both be on the committee. Now, the second way that we can look at this question is we can look at complements. So we can take a look at all of the ways that we can choose this committee. So no restrictions. And subtract all the ways that they can be on the committee. So both Brandon and Randon on the committee. All right, so let's take a look at what that looks like. If there's no restrictions, we already did this before, there's 350 ways. So if there's no restrictions, that's just 5 females choose 2 and 7 females choose 3. Now, if both boys have to be on the committee, then we're going to have the same amount of females, so 5 choose 2. But if both males have to be on the committee, that's like saying 2 choose 2. And so I won't write that out because 2 choose 2 is just 1. But that leaves us with 5 boys to choose from. And of those 5, we're choosing 1. And so 5 choose 2 times 7 choose 3 is 350. And 5 choose 2 times 5 choose 1 is 50. So 350 minus 50 also gives us 300. So a problem like this, there's 2 ways to solve. I think the quicker way is complements, but if you didn't remember to take the complement, you could also do it a second way. I did not put any at least or at most questions in here today, but remember when we're dealing with at least and at most, if we're missing only one element, that's another time when the complement comes in handy. All right, so we're going to look at a new example here. And normally in class, what I do is I read through this example, and then I have the class talk about the methods that the students use, and we discuss. Today, I'm going to read through this, and I'm going to explain what each person did, but I'm not going to give you any time for discussion because you're watching it on your own. But feel free to pause the video, take a look at the choices, and think for yourself, what was the student doing or what was the student thinking, and then listen to the explanation. It'll probably give you a better understanding of where I'm going with this. All right, so the question says, Jordan, Cameron, and Melanie were trying to answer the following homework question. So it says, the students in a school band have practiced 5 popular and 6 classical music compositions. For the school concert, they're going to choose a program consisting of 3 popular and 2 classical music compositions. And I'm going to underline some keywords as we go through this. So they're going to choose a program consisting of 3 pop and 2 classical music compositions. If the order of the compositions matters, so if order matters, determine the number of different programs which can be presented. So even at this point, you might want to think, how would I solve this problem? And so here's 3 students, and we want to look at how each of them has attempted the problem. So Jordan says, I think the answer is 11, pick 5. And then Cameron says, it's 5 pick 3 times 6 pick 2. And Melanie says, 5 choose 3 times 6 choose 2. Each student is convinced that their answer is correct, and they ask their teacher to check out the work. And the teacher asks the students to write their answers on the board and ask the class to discuss the merits of the answer. So again, at this point, we would typically be having a discussion in class. But we're going to look at what each person has done. So starting off with Jordan. Jordan wrote 11 pick 3. So what does that mean? Or sorry, 11 pick 5. So what does 11 pick 5 mean? Well, that means that she's looking at 11 songs and she's arranging 5 of them. So she's having 11 songs, and so she's arranging 5 out of 11 songs. So P would tell us that order matters, but if you look at what she's done and we look up at the questions, there's a 3 pop song and a 2 classical song that she hasn't considered. So Jordan is assuming that all of the compositions can be presented, and she hasn't considered the 3 popular songs and the 2 classical songs. Well, then what about Cameron? He's also used permutations, so that means he's assuming that order matters. So if we write out what he's got there, Cameron has 5 pick 3 times 6 pick 2. So he's definitely considered the order mattering. He's considered the 3 separate pop songs and the 2 separate classical songs. But this can also be written out in fundamental counting principle. So essentially what he's looking at is a pop song, and a pop song, and then a classical song and a classical song. Or we could have also arranged that as classical, classical, pop, pop, pop. But either way, he's looking at us doing all the pop songs together and all the classical songs together. So he's looking at all pop, then all classical, and vice versa. So again, he hasn't considered that we're selecting the songs and then we're arranging the songs. And so Melanie is the last one. And at first glance, you might think, well, Melanie can't possibly be right because it says very clearly that order matters. And we know that when order matters, we don't use combinations. But what she's looking at here is she's looking at selecting 3 songs and selecting 2 songs. What she's missing is that we need to select the songs and then arrange. So she's looking at selecting 3 pop songs and 2 classical songs. So of the 3, Melanie is the closest, but none of them are quite right. Because if we look back at the question here, our keywords were choose. That tells us order does not matter. But then right after that, we're told order does not matter. So what we actually want to do with this question is we want to choose and then arrange. So we don't see these questions too often. They're often one that we see more commonly in 30-1. It would be considered a standard of excellence question. So don't expect to see a lot of these, but it is a question that you may come across a few times. So we're choosing and then we're arranging. And so we have 5 songs. We're choosing 3 of them. So we've got 5 songs. We're choosing 3 popular songs. And then we have 6 classical songs. We're going to choose 2 of them. And then we have to arrange those. Well, once we have our 5 songs, there's 5 factorial ways to arrange them. So if I write out what that means, we are selecting 3 pop songs from 5. We are selecting 2 pop songs or 2 classical songs from 6. And then we are arranging our playlist. So think about this. If you're going into your iTunes and you want to set up a playlist, well, you might decide, you know what, today I want like 5 country songs and 3 rock songs. And so you're going to select your music first. It doesn't matter what order you select it in, but you're going to select all those songs, put them in, and then you're going to set up your playlist. And you might hit shuffle, but that's still arranging. The shuffle is still arranging your playlist. So this is us selecting our pop songs, selecting our classical songs. Now that we have that group, now we take and arrange them into a playlist. And so our answer here would be 18,000 different programs. So there's 18,000 different playlists that we could have. All right, so that is the end of the lesson. I'm going to take some time to go through a few examples from the assignment. So feel free to go and do some practice questions and then come on back and check this out. Or if you are wanting to just go straight to the assignment, do some practice questions, and then just come back in case you're struggling with a question or two, that's fine. I'm not going to go through every question from the assignment, but I'm going to pick a few that I think students have had some trouble with in the past. All right, so let's take a look at some examples here. Again, I'm not going to do every question, and if there's one that was already covered in the notes, I'm going to skip over those. We're going to look at question number 2. Number 2 says 15 rugby players line up for a team picture with 7 players in the front row and 8 players in the back row. And we're asked to express our answer in factorial notation to determine the number of arrangements of the 15 players. Well, this is a question where I would strongly encourage you to draw out the scenario because often seeing 7 in the front and 8 in the back makes us think that we have to deal with the 7 and the 8 separately. But when we write this out, we've got 8 players in the back and we've got 7 players in the front. If we think about how many ways we can select each of these players, or not select, sorry, choose or take each of these players, well, there's 15 choices for this spot. There's 14 choices for this spot, 13 for this spot, 12, and so on. So ultimately, we have 15 factorial ways. Now, I don't need to calculate this out because it says express your answer in factorial notation. Now, what if the captain has to be in the middle of the front row? So there are 8 people in the back still, 7 players in the front. but the captain needs to be front and center. And so there's only one way for the captain to be front and center, so that's 1. And that leaves us with 14 remaining players for the other spots. So that's 1 times 14 factorial. So just leave it as 14 factorial. All right, let's move on to question number 4. It says 10 students have been elected to serve on student council. In how many ways can 4 of these students be chosen to represent the school as ambassadors at the provincial education conference? Well, this one, order does not matter. Order does not matter. So this is a combinations question. So 10, choose 4. There are 210 ways. In how many ways can a president, a vice president, a secretary, and a treasurer? Well, this is an executive. This is executive. So that's a really bad way to spell executive. Let's see. Executive. So that means order does matter. And so this is going to be permutations. 10, pick 4. Definitely have more arrangements this time. 5,040. Now the last question here says 6 of the 10 students elected to student council are girls. In how many different orders can 4 of the students line up for a photograph if there must be an equal number of boys and girls in the photograph? So this is a question where we need to select and then arrange. So we need to get our committee first and then we need to take our photograph. So we're going to choose 2 girls. 2 girls from 6. We're going to choose two boys from 4. And then we're going to arrange them for a photograph. So we have 6 choose 2 times 4 choose 2 times 4 factorial. 15 times 6 times 24 equals 2,160. Now, you're going to see more questions in this assignment than you would typically see throughout. Don't expect me to give you more than maybe 1 question on a test like this. Again, this is not a concept that we talk about lots, but I have put a few examples in this assignment. All right, we're going to skip right ahead to question number 7. And it says, in how many arrangements are there of the letters in the word monotonous under each of the conditions? So monotonous, if we count up those letters, we have 10 letters. And of those 10 letters, we have 4 O's. So 4 O's and 2 N's. So again, it's always important that we know how many letters we have and how many repeats we're dealing with. So if there's no restrictions, then we're just going to have 10 letters, so 10 factorial divided by the 4 repeating O's and the 2 repeating N's. And if you remember from previous topics, make sure you have your brackets. So 10 factorial divided by 4 factorial, 2 factorial is 75,600. Well, what if each arrangement has to begin with the letter T? Well, we take T right out of the situation and we just look at how many letters are left. Well, we have 9 letters left, so 9 factorial. We still have 4 repeating O's. We still have 2 repeating N's, so that's 7,560. And again, don't forget your brackets. What if the arrangement, though, has to begin with an O? O is one of our repeating letters. So we still take O out of the scenario, and that leaves us with 9 letters. 9 factorial, but now we only have 3 O's because we've taken 1 out of the equation. So we took out the O, that left us with 3 O's, 2 N's, 1 M, 1 T, 1 U, and 1 S. So there's our 9 letters, 3, 5, 6, 7, 8, 9. But of those 9, only 3 of them are O's now. And then we have 2 factorial, and so that gives us a total of 30,240. The last part here, it says if the 4 O's have to be together. Well, if the letters have to be together, O, 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 and then that leaves us with M, N, T, N, U, and S. So we group these together, we count them as one element. So we've got 1, 2, 3, 4, 5, 6, 7 elements. So 7 factorial. we still have 2 repeating ends, so 2 factorial. And often that's how you're going to see your final answer. But we can still consider that there are 4 factorials within there. If this had been anything other than repeating O's, we would have had to write this piece out, but we have to consider those repeats. So 7 factorial over 2 factorial times 4 factorial over 4 factorial, this just cancels to be 1. And so we have 7 factorial over 2 factorial, and that is 2,520. Now, what's important for you to know is if this was a multiple choice question, you will almost never see 2,520 as one of the options. You'll actually see 7 factorial over 2 factorial. Quite often with permutations and combinations, your choices are not the final number. Your choices are part of the process. And so it's important that you don't just know how to get to the answer, but you know the steps involved to get to the answer. All right, so we're going to go through most of the multiple choice questions here, and I'll show the steps as we go. Again, feel free to pause and go back and forth or do some of the practice questions as you need. All right, a sports store has jerseys representing the 7 Canadian NHL teams and the 8 Canadian CFL teams. 5 of these jerseys have to be chosen for display in a store. The store owner decides to choose 3 NHL and 2 CFL jerseys, and then they're going to be arranged. So this is another example where we have choosing and then arranging. So we're going to choose, then arrange. And this question is actually quite clear in that it says choose, then arrange. So this is a select and then arrange question. So we have 7 NHL jerseys. We're choosing 3 of them. We have 8 CFL jerseys. We're choosing 2 of them. And then we're going to arrange those 5 jerseys. So arrange 5 factorial. So 35 times 28 times 120. And we get 117,600. And so that's B. That's C. Now, when you do these questions, anytime you're doing multiple choice, the other choices are often distractors based on common mistakes. So sometimes you could do a question and see your answer there, but always double check, did I use the right method? Did I choose and then arrange, or did I just choose? All right, number 9, a researcher has collected data on families with 3 children, families with 4 children, and families with 5 children. Each family is given a code reflecting the number, gender, and birth order of the children. For example, the code MMMF is given to a family with 4 children, where the first 3 children born are boys and the youngest child is a girl. How many different codes are required in this study? Well, we're going to have to consider the codes for a 3-child family or a 4-child family or a 5-child family. And so for a 3-child family, we've got 1, 2, 3 choices. Or means add. For family, we've got 4 choices. Or means add. 5 family choices. Now, if we think about it, we're only giving 2 codes. We're giving a code of a male or female. And so if we write this out, fundamental counting principle tends to be the easiest here. We have 2, 2, 2. Females, we either have choice of male or female, male or female, male or female, male or female. Same thing for the 5 family members. So there's 2 choices because it's either male or it's female. And so if we add that up, 2 times 2 times 2 is 8. 2 to the 4th is 16. 2 to the 5th is 32. And if we add all of that up, there are 56 different codes. All right, question number 10. The number of arrangements of the letters of the word parallel in which all of the L's are together at the end of the arrangement. So this is similar to our monotonous question where we're grouping all the O's, but this one has now gone one step further in that we're told not just that they have to be grouped, but they have to be grouped in a specific spot. So we have parallel, P-A-R-A, but our L's have to be grouped together. So I'm going to put L-L-L together. So P-A-R-A-E. The L's have to be together at the end. So we're looking at 1, 2, 3, 4, 5 factorial choices. And within those 5 letters, we have 2 repeating A's. And there's only one way for the L's to be at the end. And since they're all repeating, they all are going to look the same no matter how many times I rearrange them. So we just have 5 factorial over 2 factorial, which is 60. All right, number 11, it says a student enrolled in a general studies program at a particular university, and they must take 4 courses in the semester, in the first semester. The student must take English. They can take either math or psychology, and either 2 courses from group A or 2 courses from group B. And so we want to consider the number of 4 course programs available to the student. Well, the student must choose English, and then they need either math or math or psychology, and then either 2 courses from group A, so 2 from group A, or 2 from group B. So we consider this. We have 1 English course, and we need to choose one. So they must take English. So that's 1, choose 1. Or they can take, and they need to take. So this means they have to take math or psychology, and they have to take group A or group B. So the math or psychology, math or psychology, there are, I'm actually going to write it down maybe this way here. So the English, there's 1, choose 1. The math or the psychology, there are 2 courses. They have to choose 1. So that's an or, they have to take this one and that one. And then for group A or group B, well, to choose from group A, there are 1, 2, 3, 4, 5 courses, and they're going to choose 2. If we want to choose from group B, there are 4 choices, and we would choose 2 of them. So to choose English, it's just 1, choose 1. Often you won't actually see that part written. And we need math or psychology. That's 2, choose 1. And we need group A or group B. Remember that or means add. So this would get grouped together with an adding sign in between. So group A or group B. And so often, again, we won't see the 1, choose 1 there because 1, choose 1 just represents 1. So the ways that we can choose math or psychology and either group A or group B. And so our answer is B. Moving on to number 12. It says customer service reps at a men's designer store must wear company attire. They have a choice of 3 different shirts, 4 different ties, and 2 different pairs of pants. The number of different outfits that a customer service rep could create using these items can be represented in the expression. Well, this is a basic fundamental counting principle problem. So this is the ones that we started off with right at the start of the unit. They have a choice of 3 different shirts, 4 different ties, and 2 different pairs of pants. Now, because we've talked about selecting and arranging, it's easy to get that mixed up, but notice they're not talking about the arrangement. They're just asking how many different outfits can we have. So we've got 3 choices for shirts, 4 choices for ties, and 2 choices for pants. And so our answer is just 3 times 4 times 2. It's very easy to overcomplicate things when we're dealing with permutations, so it's important that you just break it down. All right. We're going to skip through some of these. We've dealt with questions similar. Remember, if we're looking at the number of arrangements of the letters of the word student in which the 2 T's are not together, if we're doing questions like this, what we want to do is we want to figure out all the ways they can be together and then subtract. So for number 15, I'd suggest using the complement. Now I want to take a look at number 16. Number 16 says 35 different quadrilaterals can be formed by connecting points on the circumference of a circle. The number of points on the circle is. So this is a quite common question that you see. It's actually a fairly simple problem, but it's because there's some but it seems difficult because there's some keywords we often miss. So 35 different quadrilaterals can be formed by connecting points. So we have this circle and we have a bunch of points on the circle. We don't know how many points are there though yet. But when we have those points connected, we can create quadrilaterals. Now quadrilateral has 4 sides. So 4 sides. So we have some 4-sided shapes in there. We have some dots. The dots is what we don't know. We don't know how many dots we have. We do know that we're choosing 4 at a time, and we know that we get a final answer of 35. Well, we have to ask ourselves, does order matter? If I'm drawing a rectangle, it doesn't matter where I start my rectangle, I'm still going to get a rectangle. So order does not matter. So n choose 4. N choose 4 would be my answer. Now I can use factorial notation to figure this out, but this is a question, if it's a numerical response, I would totally do guess and check. But if we wanted to break this down and solve it algebraically, we would have n choose r is n factorial over n minus r factorial times r factorial. So we're going to have 35 equals n factorial over n minus 4 factorial times 4 factorial. And then we could go through 35 times 4 factorial is 840 equals n factorial over n minus 4 factorial. Now, to break that down, we would have 840 equals n times n minus 1 times n minus 2 times n minus 3 times n minus 4 factorial. I'm thinking you can see why I said just guess and check for this one. We would have to break these down, and then we'd have to multiply all of that out. So this is not a question I would ever expect you to do algebraically because it just gets too messy. You would see one though where you had like n times n minus 1 equals 840 and you'd have to factor, but you would never see one that goes this far. So the best option for this is guess and check. And so if you guess and check on your calculator, you'll find out that 7 choose 4 equals 35. So our answer is 7. All right, we'll look at the final example here. It says a coach must choose the 5 starters for a basketball team from 6 males and 5 females. If there must be at least 2 of each gender in the starting lineup, the number of different groups of players that can be chosen is. Well, we have 5 starters, 6 males and 5 females. And if we need to have at least 2 of each gender, that means we need at least 2 males and at least 2 females. So we consider our scenarios. 5 starters, if we have 2 males, then that means we have 3 females. If we have 2 females, that means we have 3 males. So 3 males and 2 females. So we consider those scenarios, or means add. So we have 6 males, we're choosing 2. We have 5 females, we're choosing 3. Or we have 6 males, we're choosing 3. And 5 females, we're choosing 2. So if we multiply that all out, we've got 15 times 10 plus 20 times 10 is 150 plus 200 gives us 350 different ways that we can have that starting lineup. All right, guys, so normally I wouldn't go through the entire assignment in a lesson, but I wanted to make sure that you had lots of examples to work with. Definitely, this is the topic that usually causes the most challenge because we're taking everything and putting it together. But hopefully that gives you enough examples. Again, remember, I'm always available in class if you have questions. Have a great day, and we'll see you soon.